thing's going everywhere with me. And
we might have more people than chairs, so feel free to stand along the outskirts, and we can keep the doors open.
yeah, go for it. Yeah.
Yeah, thank you all so much for being here. It's really gratifying to see you all here today. I'm just going to say a few words while Hugo gets set up before we get started. So this is the first event, the first iteration of a project called Chicago Creative Machines. We're featuring 4 artists, so this Sunday and the next 3 Sundays at the same time here. Artists who work with machine learning in original and ethical and creative ways. And I'm so excited to have Hugo here to kick us off. But first, I just want to say a massive thank you to Adam and Olivia and Eddie and Alex at ESS for hosting. It is such an honor to be in this space. Massive shout out also to Kate and Troy, who are engineering. Let's give them a round of applause. They set up 8 channels in here, 4 channels out there, live streaming, microphones, everything. So great work, amazing. Yeah, I just want to say a little bit about this series and the reason that we are doing it. So machine learning is a big public conversation topic right now. I personally got started with it when I started software engineering in 2019. And what I saw when I started doing it was just this world of tools that had creative potential. Algorithms are extremely good at doing extremely specific things, and artists are good at mastering complex tools. And I thought, what can artists do with all these kinds of algorithms? And then I discovered lots of amazing people like Hugo and Hunter Brown, who's going to be here next week, X.A. Lee, who's going to be here in mid-March, who are doing creative work, building their own machine learning tools, concerned with the ethics of it, concerned with the originality of it, and wrestling with all these issues. And I was like, how do we bring these minds together and share all this great knowledge and have a great conversation about machine learning and enjoy their art? So that was sort of the impetus for Chicago Creative Machines. I was just checking this morning, and so GPT-4 came out less than a year ago, y'all. Less than a year that's existed, and the conversation has just taken off in all kinds of directions. And so we want artists to be part of that conversation. So just want to brief one sentence definition of machine learning. I don't know, I'm sure a lot of y'all already work with it, know about it, but some of you don't. So here's my mental model of machine learning, and I know that Hugo will share his own. But when I talk about machine learning, what I think about are statistical models that take in data. But unlike a statistical model that a statistician goes in and programs and tells the computer what to do, a machine learning model is a statistical model that the computer learns on its own from the data that you give it. So the computer has a really active role in formulating this model, and so there's a lot of uncertainty, probabilistic, statistical sort of processes going on, and the machine can surprise you with interesting things. So that's kind of the joy and the fun and also the risk of machine learning. So how today is going to work is Hugo is going to share with us a little technical talk about his tools, how he's developed them, what he's using, and then we're going to take a real quick break, and then Hugo is going to do a performance for us of his work, his really amazing work. So I just want to give Hugo a proper introduction because it's so amazing to... Oh, that's me on a string. That's so amazing. It's so amazing to have him kicking us off. So Hugo is a computer musician, audiovisual artist, composer, programmer, and computer scientist. His creative practice includes improvised music for guitars, electroacoustic compositions, live coding, interactive installations, which you just experienced, and bespoke interactive musical instruments. His work is inspired by the appreciation of and interaction with the natural and human-made processes and ecologies around him. He's a PhD candidate at Northwestern University and doing research at the intersection of music, and applied machine learning, and he's designed new interfaces for creative expression with a focus on sound. So please give it up for Hugo. We're really excited to have you
Howdy. Thank you, everybody, for coming. I'm really excited to do this. I'm trying to get the display to work, so everybody.
Isn't the projector voice activated?
Yes.
I don't think so.
Yeah.
Did you undo the USB-C to your computer?
Let me try that.
Oh, okay. See, it came back now.
Oh.
Okay, we're sort of searching now.
Okay.
So
Hey.
detect.
Hey, beautiful. Tech, computers were a mistake? Question mark. Cool. Yeah. So, my name is Hugo. As Molly said, thank you so much, Molly, for the intro. And I'm here to talk about just generative sound for the sonic arts and a little bit of my practice with these tools. Cool. Yeah. So a little bit about me. I'm like Molly said, sound artist, improviser. Programmer, guitarist. I'm originally from Tegucigalpa, Honduras. I moved to the States when I was 17. Getting my PhD in computer science at Northwestern, where I do research around building controllable and artist-centered interfaces for sound. Cool. So, as we all know by now, neural nets are super powerful at modeling signals. This is actually like a pre-ChatGPT generated image. This is a Google thing called Deep Dream, and I use it as an example for like the expressive power of neural nets because it's like actually a super. The way that this algorithm works is that you give it some image, and then you train the model to recognize like a very specific object. I think for this one is fountains, and then you give it some random image, and it'll go through the image. And it'll try to find fountains everywhere. It'll look at the pixels of the photo and go like, oh, this kind of looks like a fountain. I'm going to make it look more like a fountain. And then you end up with something like this. So they are incredible at doing pattern matching, and they can be super expressive as a tool for making art. And the problem that we're seeing right now is that there's a bunch of consumer-centered interactions from big corporations that are promoting. And the interactions that I see for these are pretty shallow. And they don't really lend themselves to like a prolonged artistic process. But there's people doing really awesome work with generative sound. These are 3 artists that I kind of want to share with y'all that do pretty cool work with generative modeling and sound. This first one is Exorcismos. Exorcismos is a sound artist, technologist, and electronic musician from Tijuana, Mexico, working in the fields of computer music and artificial intelligence. And as Exorcismos, he crafts kind of like uncanny links between ancient technology and state-of-the-art technology, channeled through a sort of decolonial theory lens in the context of contemporary music. Whoa, that was loud. Sound check. Cool. Next up is databots. Databots are famous for their like infinite streams of music, usually trained on metal bands. This stream of metal that I'm about to play here has been running since 2019. And we're gonna hear some probably never heard before sounds. If it pulls up. Yep. I mean, it's just going to keep going. You can tune in at home if you want. You'll probably listen to a different version of it. This is probably my favorite sort of piece of music that's made with a generative sound model. This is Holly Herndon and Jaylin, and this is tune called Godmother, and it's a bunch of generative models trained for voice, I believe, and yeah, they sort of organize that sound into really, really nice sounding texture. Cool. Yeah, and all of these examples are like for the people that like high quality audio. All of these examples are really kind of like fussy on the high frequencies, and that's like a very easy tell for what's generated sound and what's not. We haven't really figured out how to nail those high frequencies, so all of that detail kind of like above, like where you start to hear the S and stuff like that, above that, it starts to get really fuzzy, and it kind of like gives that the generative AI sound, if you will. And so yeah, this almost fuzzy quality. Not sure if I love it or hate it yet. So yeah, my motivation for generating sound is actually guided by the same principles that have guided computer music for almost 100 years now. As an instrument designer, my dream is to be able to make an instrument where I can control like any sound material with an interaction that feels very natural and embodied to me. That's kind of the dream here. And of course, there's like an entire line of discourse that talks about how like there's affordances and limitations in musical instruments, and that actually guides the music that we end up making. So it gets pretty interesting once you start thinking about that ideal instrument where all of the sounds are possible and they are affordable. Like, what does music start to sound like then? Cool. So take a little detour here and start talking about how do you make sounds with machine learning. And I'm not gonna get super technical because it's like a whole rabbit hole, and I would love to come back here at some point and spend a couple hours just teaching people how to code this shit. But I'm gonna cover sort of like the grand concepts of what we're doing here when we generate an audio signal with a machine learning model. So we start by realizing that audio is an incredibly high dimensional signal. And that's a problem for computers, and I'm going to explain sort of like what that means. And what that means basically is that we need thousands and hundreds of thousands and millions of data points to be able to reproduce audio in a computer. So 1 second of single channel mono audio, that's going to be 44,000 data points. 10 seconds, that's going to be 441,000 data points. 5 minutes of stereo audio, so that's like your average pop song, that's 13.23 million data points. And that's a lot to process for a computer. And just kind of an illustration for how high dimensional sound is. Here's a talk that I really like.
There's no points there now. There's a lot more points. In fact, you can't even see the individual points. We sampled at 44,100 points per second, or 44,1,000 hertz. And that's just a huge amount of data there. So we can't do much with what we're seeing right now. We're going to have to zoom in to actually see what's on the inside here. So let's do that. Let's zoom all the way in from the second scale down to the millisecond scale here. And as we get closer and closer, you can actually see the individual sound waves that were used, or that came out of that saxophone and went into your ears. And this is what your ears were vibrating like, back and forth in this pattern. Now here, if we measure the distance between these two peaks, not these points, but these two peaks here, we can actually see there's a duration in there in milliseconds. That's 5.7 milliseconds between peaks. And if we do a little bit of math on that again, do 1 cycle divided by that, we can find out even the frequency of the note that the saxophone was playing. So just from measuring that waveform over and over, we're able to find out the note. And I think that's actually an F, so that we can find out what musical note was being played there just by doing some math. But let's keep going even deeper. We're still only looking at the milliseconds level. Let's go from milliseconds down to microseconds, where we'll be able to see the actual samples. So now that we're super zoomed in, the actual samples look like little points along this graph. And we can measure, again, every single point at the microseconds level. And this gives us a representation of the audio. And here's the real secret that I want to tell to you all today. This is digital audio. This is all it is. Digital audio is really just streams of numbers. Nothing too complicated.
I'll leave it there. So yeah, we have a lot of data to work with, and if you think of a machine learning model that's going to try to be making these 13 million data points all at a time, it becomes super unwieldy, and you end up needing machines like this one to be able to do any kind of stuff like that. And it still is not feasible. So we had to come up with like a kind of a solution, which is called tokenizing a signal. So in order to generate audio first, we need to compress it such that we don't have 13 million points for 5 minutes. We want kind of roughly like 500 points for 10 seconds of audio that feels nicer, that feels more manageable. And for that, we're going to use these two neural networks. So these are AI models called a tokenizer and a detokenizer. And the job of this model is very simple. It's very straightforward. It's just to reconstruct this signal. So we want to be able to come from this raw audio signal, take those numbers, process them, and get this representation in the middle that's thicker, it's coarser, so it's less numbers, less data points, and sort of like represent more high-level concepts about the audio than rather just this is how the air is vibrating right now. And you want to be able to pass that through that detokenizer to get an actual that actual sound back in. And it doesn't work perfectly, and this is where we actually start to lose those high frequencies. So to illustrate, here's some raw audio. So it's going to go through that tokenizer, get compressed into that sequence of acoustic tokens, if you will, and then we're going to run it back through the tokenizer and hoping to get the exact same sound. We want to get the exact same sound out of it because we want that token representation to be basically a replacement for all those 13 million numbers, right? And it's not perfect, but it kind of gets us there. Again, really fuzzy on the high frequencies. So in the audio space, we represent this, these tokens kind of like as a sequence, right? Like kind of like we're used to with audio samples, where like, as you stretch them out over time, you get longer audio signals. And then once you have this compressed signal that can sort of represent this super complicated sound, it becomes kind of straightforward to generate new sounds. With the same engine that, if it powers ChatGPT and powers all those like image generators. Once you have this tokenized representation, that's kind of what they all have in common. If you're going to generate images, you're going to convert the images to tokens and then the tokens to images. If you're going to generate sounds, you're going to take the sound, convert it into a token, and then convert it back to another sound using this framework that we talk about. And I'm not going to talk too much about language models because there's, they're super popular right now, and there's lots of like really good resources for how they work. But roughly, for our purposes, they are generating everything bit by bit, patch by patch. So you go token by token. Maybe that's like in 10 millisecond increments. Or if you're generating an image like you see here, you're going to go, from the top corner to the bottom corner, like little patch by little patch. And every time you're at, every time you're like at a patch, you need to ask the model, and the model here is like very much in the sense of a statistical model. It depends on the statistics of the data that it saw. It's basically going to give you a probability distribution over what's the most, next token, the most likely next token. So if we're generating an image of a taper made of an accordion, we're basically going to scan through the image patch by patch, and at every patch I'm going to ask, given all these patches that I've seen before, what's the most likely next patch? And we're going to go, over and over going through this probability distribution. And again, this is just our reflection of your data. The how you learned this probability distribution, like how you learned what the most likely next thing is, was by looking at all this data and sort of learning the probabilities of that data. So data is like 90% of the game here. Sort of on this like text to stuff world that we're talking about. Everybody's talking about text to audio, and all these big corporations are putting a lot of money into their text to music systems to sort of make products out of it where you punch a button and get 5 minutes of music out of it. And I don't know how I feel about that because the state of the art seems to be writing about music where you take some text prompt that looks like this. Fusion of reggaeton and electronic dance music with a spacey, otherworldly sound induces the experience of being lost in space, and the music would be designed to evoke a sense of wonder and awe while being danceable. And then you would get something out like this. And, I guess that's great if you're playing for a bit and you're trying to, maybe just capture like a generic mood. But as a musician, this kind of interface becomes super frustrating really quick, right? I don't really think about sounds in terms of sentences in English or in Spanish. So when I'm thinking about musical ideas, and I think a lot of the musicians in the room will probably feel the same way, I'm usually thinking in terms of like very abstract structures, like rhythms and pitch contours, and more generally just gestures, right? Stuff that I just decide to like manifest into this continuum of sound that can't really be easily described in the English language. So, super, like here's an idea I had the other day. Help me write that down into a sentence, please. So yeah, writing about music is like dancing about architecture. And this is a famous quote that is attributed to various artists and captures, kind of like how I feel about these text-to-music systems. Here's another quote from Trevor Wishart, who's an incredible computer music composer, that, kind of reinforces this idea that we can't really describe music in terms of words. So if you imagine kind of a world where everybody starts making music by writing text prompts, you would, kind of like an instrument, right? The affordances of writing text prompts are going to like manifest into the music. So you would probably notice that the music of the world on average just starts to lose nuance on things that you can't properly describe in the form of text, right? If you can't put the nuance of the rhythmic structure that you want in your song into a text prompt, then you lose the ability to have control over that, and then everything just sounds like the average rhythmic structure in your data set, right? Because again, it's just a probability distribution, so it's just going to look for the highest probability thing, unless you can tell it exactly what you want. So this kind of like brings me to my whole point, is that sound prompts could feel more natural than text prompts, right? I could use a sound to describe another sound that I want, and maybe I could use that to create a sound that I want to make. So that's what I did. We built a generative ML system for creating sounds guided by other sounds. And that's kind of the research that I've been doing for 2 years now. So this is Vamp Net. It's an ML model we made a couple of years ago, or last year. I don't know, to time. It generates audio by filling in the blanks. So there's no text prompt here. It's a sound prompt. You give it a sound and you get a sound out. So we can start with some input sound, and this is how you train it. You start with some input music that sounds like this. And then we can take that signal and encode it into acoustic tokens like we talked about. Now we have like a thicker representation that's easier to handle. And then we can blank some of those, right? We can sort of mask some of these. So now there's some blanks, and we know what the true answer is, right? Because we heard the original song. We just have to train the model to fill in those blanks. So then we end up with a masked signal, which sounds like this. So all those blanks that you're about to hear, that's where the model is going to fill in. And then, we train Vamp Net to fill in the blanks, and then we get a generated sound that, is a variation of the original, but not quite, because it takes advantage of that fuzzy like probability distribution kind of behavior that we get out of generative models. So it sounds like this. So we kept the rhythmic structure, kind of some parts of the original, like the original piece of music, but we got something slightly different. VampNet is kind of like able to take a library of sounds and present them to you as kind of like a malleable probabilistic material instead of like straight up samples and sounds that are just solid and they're just set in stone. And that's kind of like what I really love about it. And there's kind of like a whole world of techniques that you could use to, make different kinds of sounds that you could take advantage from working, when working on a composition or something like that. We found this out almost by accident too, which I'm pretty happy that we did. The first thing that you could do with VampNet that I already kind of showed is create a variation of a sound. So you give it a piece of music. Right, you heard that? then mask a portion of these tokens, and then how many of these tokens I'm going to mask, or how many of those blanks I'm going to give it, that's going to give it more or less freedom to fill in the blanks. So this is more of a more constrained mask than the previous one. Happens faster. And then you get something like this. Which is kind of there's other cool things, like interpolating between two sounds. So I can give it tokens from two pieces of music, completely unrelated to each other, and then put some blanks in between them and tell the model, make a cohesive transition between these two things, or make a cohesive blend between these two things. So I literally took the music and just like chopped it up together. It sounded like this. And then I ran it through Vamp Net, and I got something like this. I don't know what that bark at the end is. Y'all, I have given this talk like 10 times, and that bark gets me every time. Yeah, and here's my favorite part. You can fine-tune it on your own music. You can give it specifically what sounds you want to shape. And then shape those sounds, right? So I can, take some training data, which is, in this case, my drum and bass music. And then I can give it some input gesture, again, just a rhythmic structure, maybe some timbre guidance, something that sounds like this.
I'm not quite fond of statistical models or their tendency to make me sound like their skewed definition of normal. But I do enjoy getting to listen to what could have been just as much as what is.
And then run it through that Vamp Net that only knows drum and bass. It actually only knows this one song. And then is going to be forced to reshape that material into something composed of the material that I gave it to train. So it's going to sound like this. So yeah, we're taking like sound material that already exists and we're giving it a different shape. That's kind of what we're doing here. And we can fine tune it on sound textures, right? It doesn't have to be music, and I actually prefer it not to be music. Here's a counting machine. And here's a gesture. Here's a sound that I want to, here's the shape that I want the material to be in.
Tres tristes trigas tragaban.
Run it through the model, and then we get, yeah. So we gave it shape. We gave that sample of a counting machine, we gave it the shape of the gesture that we made. Here's another one that I found out by accident and ended up being one of my favorite things, kind of like opinionated time stretching. And what I mean by this is, when you take a signal and, you put it through logic and you stretch it in time, you want the same signal but slower, right? You could try doing this with Vamp Net, and instead of, just stretching the signal, you just take the signal and put a bunch of blank spaces in between, the little blocks, tokens. And what you end up is basically giving the model freedom to fill in the microspaces between, the stuff that you're stretching while still keeping the long-term structure of that original gesture. So here's an example of this opinionated time stretching. So here's the input. This is me clicking my tongue. This is if I stretch it 5 times. So we get, stretch it 5 times with, I was not going to do the math, with just, regular signal processing. You just put it up in logic and do some time stretching. Same sound. And here's what happens if I stretch it with Vamp Net. So this is kind of like the opinionated time stretch, and this model is trained on I think this, yeah, it's percussion samples and like some of those like counting machines and some of those other like very like percussive things. And this is what it sounds like. Again, we're just time stretching it. And it still follows that pace, right, of my clicks. Yeah, so yeah, that's an opinionated time stretch for sure. Here's another thing. I can morph two sounds. I can go from one sound, one texture, I don't know how to describe this. Yeah, one texture with its own timbre, with its own rhythmic structure, and convert it into a completely different texture with its own timbre and rhythmic structure, sort of gradually over time. And I can do this just by using a prompt. So I kind of wanted to show you. This is the actual. This is what the actual tokens look like. Those other ones were kind of like an illustration, but this is roughly how they're like structured in time. This blue part is the mask. So that's all the parts where it needs to fill in the blank. So it's going to, if you see here, we have a lot of stuff here. We're giving it a lot of hints here, but as we go over time, we make those sparser and sparser, so we give it more and more freedom to fill in those blanks. So it's going to impose more of the characteristics of its training data as it goes over time. So here's my input. Yeah. And yeah, here's that output. So we're going to hear it sort of like gradually lose its original rhythmic structure and turn into the rhythmic structure of the training data. Yeah, it's almost like it gives in. It's like, here you go. Yeah, just do your thing. And then this other cool thing is that now sound is a malleable material, and it's not really the sound that was, but it's like the sound that was and a bunch of other possibilities, the sounds that could have been, right? That's kind of like how I think about it. So we can now listen to like multiple possible realizations of a sound at once, right? And this is kind of like a technique that I use a lot in the piece that I'm gonna show later. But yeah, I kind of like thinking about like, yeah, I'm like listening to like the multiverse of this sound, like all the things that it could have been. So here's this input gesture. Oh. Very bad beatboxing. And here's the output, again, using this percussion model. And you should hear one sound here and the other sound here, hopefully, if I did it right. If not, you'll hear it in the piece. Yeah. Cool stuff. Yeah, and this specific part kind of brings me to like an important point, and it's that generative models create so much shit that like we won't be able to listen to all of the output, ever. There's just too many sounds that it can make. So this concept of the economy of selection becomes like even more important, which is, now that you can get to the point where you can make basically any sound that you can, choosing which sound to make becomes even more important. And I like to say that working with generative models is almost like digging through a huge pile of trash and then finding some gold and going like, hey, I'm going to use that for something. Yeah, here's another quote by David Cope, who's very famous for his experiments in the 80s, trying to make an AI system to make, I think it was Baccaras and sonatas and other things like that. And yeah, like this economy of selection is like even more important now. Yeah, Vamp Net is open source. I've made the code for training the model, open source, and you can fine-tune your own model on your sound library if you would like to use it. I'd say give it a try. Let me know how it goes. And yeah, I'm happy to take any questions at this point. If anybody has any curious about anything.
I was going to ask you, did you experiment with different software to come up with your choice of Vamp Net? Or are there others out there that you experimented with?
Yeah, well, there's a couple of models. In terms of like architectures, there's a couple of techniques. This one that I talked about with the tokens and stuff is based around transformers, which is the stuff that you hear with ChatGPT and all that stuff. But there's also like another family of techniques called diffusion models. You hear those thrown around a lot too. And I haven't actually messed with diffusion models, but I kind of like really leaned into this because this thing with the tokens where I can mask them and make it fill in the blanks, that has kind of like really opened it up for me so that I can like give it gestures with just my voice and be able to like morph the sound material that way, that I haven't really seen anybody else do yet, which I'm kind of excited about. Yeah.
What's the code book level that's mentioned on some of the slides?
Yeah. So I had a slide about this, but I didn't think I was going to have time to get to it. There we go. This is the one. Yeah, so codebook levels. Oh, never mind. Codebook levels. Never mind. 1 second. Need to unhide the slide. Yeah, so it's these tokens are two-dimensional, which means that you have the time dimension. So as you add more tokens in this time dimension, you get longer audio that lasts more time. But we also have, and this is actually kind of very important for the actual generation part, this part where I control it with my gestures. And it's that these are two-dimensional, so there's this kind of like other dimension here. So there's multiple code books, multiple tokens for one piece of time. And the bottom ones contain sort of like, not really the low frequencies, but kind of just like the core structure, like the semantic structure of the sound, sort of like what sounds are there in the audio and when do they happen. That's kind of the information that happens at the bottom. And then at the top, you have kind of those details about like the high frequencies, which is, we're not really good at modeling those top codes right now. We're not really good at generating those. We're kind of good at modeling the bottom ones, but the top ones still sound super wonky. And to give an example, this is what it sounds like when you use all codes. So this is all of the codebook levels. And then if I remove and I just leave the two bottom levels and try to reconstruct the sound, I'm gonna get, again, the same rhythm, the same gesture, the same structure, but most of the actual tone of the sounds are gonna be gone. So you know what sounds are happening when they're happening, but you don't really know like exactly what is the identity of that sound, or like at least the model doesn't. And that's kind of what I use to do all these like voice promptings and voice control, right? If I remove all of these top levels from my voice, all that remains is just kind of like this rhythmic structure, right? This gesture. And then I can use that to generate some sound. Yeah. Anybody have any? Oh.
You said you discovered like some of the capabilities of it by accident.
Yes.
How did that happen?
Because this thing wasn't working. That's the story. It wasn't working, and didn't work for 6 months. And I was at an internship at this startup called Descript, and they went like, yeah, I mean you can do a project of your liking, and I went like, yeah, I'm gonna try doing this. And then 3 months in, I couldn't get it to work, and then it was like, okay, what are like some really dumb ways to check that it is working? So I'm gonna start removing a token from the middle and have it fill in the blank there. And it worked. And yeah, that's the story. Yeah. Molly, I think you had a question.
Yeah, I'm curious how your work with machine learning has transformed, like how your musical practice was transformed by your working with these things over time.
Yeah. It's honestly just gotten me really into electroacoustic music and into computer music. I really I might talk a little bit more about it when I show the fixed media piece, but I've been kind of obsessed with this idea of like the mouth as the interface between me and just every sound that I can imagine or I can collect. So yeah, I have this thing now where I want to collect all of these sounds and I want to be able to shape them with gestures that I make with my mouth, and that's kind of where I'm at. Yeah. Hi.
So there was your Zoomies piece.
Yeah.
You trained the piece on, right?
The cat.
You trained the model on.
Yeah.
So there's this technique that I've been seeing where people will fine tune like a language model, but first it's been trained on like a bunch of text, and now you're training it on a little bit of text to give it like a style, but it's sort of seen language before.
Yeah.
Were you talking about a model that had been exposed to other music and you fine-tuned it on only this song, or were you training it from scratch and that's the only data that model had ever seen?
Yeah, no. This model has seen a lot of music,
Okay.
but it's seen a lot of music, and the way that I try to set it up is such that the reason that I use all of that music is just so that the model has an idea of how sound works, right? Because like there's rules in this physics of the universe that we live in where like some sounds can happen and some sounds can't, right? What helps when you give it all of that data is get an idea of like how are sounds shaped, what's an attack, what's a decay, what's a sustain, this fine-tuning part, this fine-tuning part, it's more like I'm giving it this 5 minutes of music, and now that it has all this understanding, I'm going to make it memorize this piece of music and be it like the only thing that it knows. And once I have this model fine-tuned on this song, every time you sample it, every time you use it to generate something, you're always going to get a skewed version of the song. Yeah.
So you're composing different embeddings. You've got sort of lots of sound and then these additional train. Okay.
Yeah. I have sort of a model that understands sound, and then I fine-tune it so that it makes specifically the sound that I want it to make. Yeah, because otherwise, one second. Otherwise, the model tends to resonate, right? It likes to fall into the average of the data set, right? And I don't know about y'all, but I don't really like my music to sound average. So yeah, I think you had a question.
Yeah, where is your curiosity leading you next in the development of Vamp Net or just machine learning as a whole?
Man, I wanted to work in real time. That's one thing that's been kind of like bothering me, is that it takes 10 seconds to process 10 seconds of audio. So that means that I can do an installation like that where you can record 10 seconds of sound and then 10 seconds later you hear it transformed and stuff like that. But I can't really make a gesture like in real time and have that manifest into something yet. I think that would be really cool. Yeah.
Let's do one more question, and then I know there's going to be a lot of conversation, but let's do one more question and then take like 5 minutes and then come back for the performance if that's cool, and then we can have time afterwards to talk.
Yeah, that's
The
okay.
question's not that good. Pick someone else.
Hi, yeah.
Hi, I just wanted to ask a question on, you said you made Vamp Net with transformers,
Yeah.
and that you haven't touched on like the diffusion side of generative, because it's kind of, when you talk about Vamp Net and like filling out stuff, it kind of reminds me of like stable diffusion, where I don't know if you've seen those like Adobe ads where they're like, oh, I'm gonna like, here's a photo, I'm gonna like, like highlight some part and have it like, and give it a touch prompt, like make this man like hold a cat or something, and
Yeah.
it generates that.
Yeah, I mean, it looks cool. All of those diffusion techniques look really cool. They also look more lightweight. Like maybe I wouldn't have to carry this thing around. But again, like, it took me a solid 8 months just to get this thing to start making any kind of sound. And I'm still, I'm still trying to get try to get it to work better. So yeah, it's kind of a rabbit hole, and I'm kind of like, I'm in this world for now.
I totally understand like your intuition for transformers though, because transformers, the point of transformers is here's a sentence, what's like the highest probability of the next word.
Yeah.
And that works in music where, here's some sound, what's the probability of the next sound. So I just want to point out like there's a lot of interesting parallelisms.
For sure.
Great, thanks. Why don't we give Hugo a 5-minute break to set up for this performance? Go check out the installation. Yeah, let's clap. forefront of this research, y'all, so it is amazing to have him here presenting. Let's give him some time, chill for like 5 minutes. The restroom is out here. We'll come back for a performance in like 5 minutes. Ready for part 2 here. Let's give Hugo another round of applause. So in addition to being an incredible researcher, engineer, thinker about machine learning, Hugo is of course also a great composer, improviser, and artist. So we are about to get to experience some of his creative work that he's made with Vamp Net and also a live improvisation. So Hugo is going to be presenting a composition he's made with Vamp Net, an 8-channel fixed media piece, which is why you see this lovely array of speakers around us, and then he's going to perform live. So let's give it up for Hugo as artist, as engineer.
Sweet, yeah. So I'll start by, I'm going to show actually 2 recordings of pieces that I've done with Vamp Net before. One with Mike here on the sax, and the other with some percussion samples. And then I'm going to show the fixed media, talk a little bit about how I made it or why I made it, and then play a little live set with a machine learning instrument that I'm going to show later too. Cool. Yeah, so this first work is called Confluyo Yo. It's a piece of improvised music with Mike on the sax here, where there's a saxophone player improvising, and again, sort of like around that same concept of hearing the resonances of the training data, we're sort of going to hear the saxophone build up texture of bird sounds over the course of this improv. So right now I'm like really obsessed with this thing, where I can, my mouth as the interface between me and, all of the sound that I can collect. And why I'm doing this is because our voice is kind of remarkable at imitating sounds. And here's a quote from Trevor Wishart that I love.
And the idea of sound morphing, of transforming one sound into another, and discovered that my voice was the most powerful technology I had, because with the voice you can imitate almost anything. So not having a computer to take the sound apart, I could imitate the sound I was trying to make. Perhaps it was a bird sound, perhaps it was a
machine sound. I should have caught it too early. But yeah, so I kind of have this process in mind where I collect, tens, hundreds, thousands of sounds, and I train a model of these sound materials, a model of these sound materials, to turn these materials into something that I can, shape with my voice, so that I can perform a gesture with my voice. And this creates a new sound where the material bends to follow the shape of the gesture, using the model as that expressive object. And I want the outcome to be I can sort of create and shape entire sound environments using just these vocal gestures, which makes it kind of a very embodied experience. And I also want the material to eventually bite back, right? I want the material to start shaping my gesture and impose properties of that material into the resulting sound. And that actually causes a lot of surprisal and the composition process. And it was truly like a joy to work on this a channel piece, because I kept being surprised by the sound that was coming out of the network. I was hoping that my gesture would come out into the model and it would be perfectly shaped into this thing, but a lot of the time the material just didn't want to bend that way, and the material just ended up being its own thing. So yeah, here's this composition. Ended up calling it World of Mouth. It's a 8-channel electroacoustic fixed media for voice and Vamp Net. Yeah, let me pull it up. Sure, probably. Cool. Here's World of Mouth, new channel. Thank you. Cool. Yeah, thanks for listening. I'm gonna play a solo set of improvised music using a machine learning tool that I didn't make, but I really want to share with everybody because I think it's amazing and I think it's a great way to get started, get your hands dirty if you want to start doing some machine learning with sounds. This is called Audio Stellar. It's made by some folks in Argentina, and it's an embedding space sampler, and that means is you can give it a huge sound library, got like 10,000 sounds in there, and then it'll project those sounds according to how similar they are to each other. So you end up with a map of basically that sample library, and what I really like about what they did is that they created these like engines that go with it, that sort of are like little like spaceships that you can cruise around the embedding space with and like sample sounds using different sorts of like gestures. So yeah, I really like it. And you know, if you're curious about machine learning and what it can do for your creative practice, this is a pretty great place to get started. It's like an easy download. It took me like 10 minutes to set it up. But yeah, let me see if I can share it on the screen so that y'all can see it as I use it. Oh yeah, and something really cool about this is like just out of chance. This map that I did of these samples ended up looking like the map of Honduras, which is where I'm from. So, just life, I guess. Don't even know. Cool. Let me see if I'm all set up here. And I'm set up here. One sound. There we go. Cool. Thank you. Thank you, everybody, all the ESS folks. Thank you, Molly, for having me. Thank you all for coming. I mean, this was so fun to do. Yeah.
Yeah, thank you all so much for being here, participating in the first Chicago Creative Machines event. Now's the time where I plug the fact that the next 3 Sundays here at the same time, there are 3 more artists who do great work that's totally different with machine learning and sound and video and text coming to present. So please come back or stream online. Thank you for those who tuned in online. Next 3 Sundays, 2 p.m. Next week, we're going to have Hunter Brown, who is a laptop improviser who has created a custom instrument in Super Collider and has built a couple different machine learning tools into his improvisation setup. So he's going to be sharing those tools with us and then performing for us. The next 2 weeks after that are X.A. Lee, who is a generative video artist who works with what she calls post-consumer material, so sort of images around consumerism, and she's going to be presenting her generative video work around that. And then the following week we'll wrap up with Julie Zhu, who is a text and video and sound artist who works with the sound of writing. And so it's going to be an amazing next 3 weeks. Please come back, please bring people, and thank you for participating, thank you for coming, and thank you, Hugo. Engineering today. Grab some stickers on the way out. They're on the table out there. See you next week. Woo! Cool. Yeah.